Alright, I'm Kalu, and I'm going to be doing the car driving along a curve problem. So we have a wedge-shaped road, basically, with an angle here of 30 degrees. 30 degrees. There is a car. It's here. And it has a mass of 2,510 kilograms. And it is driving along a curve with a radius r, which is 50.0 meters. And the coefficient of static friction between the car tires and this surface is 0.43. So, we're trying to find the maximum speed in meters per second at which the car does not slide up the rim. So, let's break down some of what this means. So, this symbol here, mu s, that's a way that we relate our frictional force with normal force. So normal force is, let me draw a stick figure here, that's pushing a wall. Here's our wall, stick figure pushing the wall. So let's draw the force of the person on the wall. So that force is, sorry, that's a little slanted, it should be nice and perpendicular to the wall. So that's the force that the person is pushing on the wall. If that were the only force in this situation, then the wall would be moving in the direction of the net forces, which is to the right, but it's not, so there's some kind of normal force. If we were saying our wall is going to be stationary, then there's some normal force. It should be coming back right at this point, but it's going to overlap with this, so I'm just going to move the symbol up here so it's easier to see. So this is our normal force. It is perpendicular to the wall. All the normal forces are going to be perpendicular to the surface. So it's also happening here. This person is standing on the ground, and this is the force of their weight on the earth. And then the earth has some kind of normal force pushing back up. These normal forces should have the same magnitude as the other force in the case that nothing is accelerating. So that's what normal force is, and that helps us figure out friction, the frictional force. So this is our symbol for frictional force, this fancy F. So that's going to be somehow equal to the normal force, but they're not going to be the exact same number. That's why we have our coefficient of friction. So this is the coefficient of static friction because the car tire is moving forward and back, but not side to side, so effectively it is going to be it's going to be stationary compared to in this direction. So that means it's going to be, also if you have a wheel, like this, sorry, very lopsided wheel, but this point is going to have contact. It's not going to slip against the ground. It's going to roll to the next point. So this point is going to have constant contact with the ground while it's touching the ground on the tire. The tire isn't slipping, so you can see how each individual point isn't going to be slipping. So that's why we use static friction. If it was slipping, we'd use mu k, which means kinetic. But we're going to have mu s here. So that means it's going to be proportional to the normal force. So we're going to use this equation later. Also, I'm going to have to run through some basic trigonometry. So trigonometry is how to figure out certain ratios of side lengths. but only for a right triangle. So there's sine, cosine, and tangent functions. And so let's call this here angle A, and this angle B. So a way to remember how these work is the mnemonic so, ka, toa. So this means that, so O means opposite, A means adjacent. So these are talking about sides of the triangle. And H means hypotenuse. My drawing tablet has some lag, so my handwriting's pretty bad. But, so here we go. Let's see. This is our hypotenuse. It's always going to be that. But the opposite side for angle A is going to be this side over here. But for angle B, it's this side over here. So it all depends on the angle we're looking at. So, if we were to say sine A, that's going to be the ratio of opposite to hypotenuse, so it's going to be equal to O over H. So sine is the S, and then it shows you which of the sides you want. C for cosine, and then the sides you want. T for tangent, and the sides you want. So it's going to be function of the angle, and then side as the numerator, and side as the denominator. So these are always going to be ratios. So even if, no matter the size of the triangle, as long as it has the same angle, it's going to have the same sine, cosine, tangent ratios. So if we knew what sine A, let's say we know what sine A is, and we know what H is, but we don't know what O is. We want to figure that out. So that means H sine A is equal to O. So I just multiplied both sides by H, right? H cancel out, and H here. So that's what we get that. So we're going to be using these a bunch, and for this problem, to figure out components of our vectors, which is the next thing I'm going to run through. So a vector means it is something that has both magnitude and direction. So magnitude, for a vector, you're going to symbolize it typically as an arrow. So here we go. Oops. So let's call this our velocity vector so that we can figure out so we can look at centripetal acceleration next. So here you go. That's our vector. Its magnitude is effectively its length, and its direction is the way it's pointing. Pretty self-explanatory. But let's say we take this vector and we turn it into this vector. So here we can see that its magnitude has changed as well as its direction. So the change that we've done is we've added a new vector, this one here, to this one. So that change in velocity is going to be acceleration, because acceleration is change in velocity over change in time. So that's the formula for average acceleration in order to get, that's for average acceleration. So let's look at a particle moving in a circle. So, particle. It's got certain velocity, but it's moving along some circle. So if the particle is over here, its velocity is going to be like that. So let's say it's always going at the same speed, meaning that the magnitude of the vector will be the same, but its direction has somehow changed. Okay. So there's hasn't been a change in magnitude, but there's been a change in direction, meaning that there has been some acceleration that has happened, even if it wasn't magnitude. So, let's say we have, let's make a little wedge here of that circle. So we have a particle here, and a particle here. We have velocity 1 and velocity 2. And let me draw that out over here a little bigger so it's easier to see. And I'm going to put their ends together. So if we were to map all of the velocities that are happening here, I'm just going to draw lines. It's going to look like this, all around the circle. And then in order to get from one to the other, this is your change in velocity, this little vector here. And if you were to map every single point along the circle, all of those, your delta v's would get very, very small, but they'd map a circle. They'd map the circumference of a circle. So your delta v's would be the circumference of the circle, which has a radius of v, so that's going to be 2 pi v. But also, so we have our delta v, so delta v divided by delta t. And then our t, let's say that's just the time it took to go around the circle. But what is that time? Know that distance is equal to velocity multiplied by the time it took. So if you go 3 meters per second, if you go for 2 seconds, then you go for 6 meters at that speed. So the distance we've traveled if we've gone around the whole circle is it's called as radius r. So that means this distance that we've gone around is a full circle, so that's 2 pi r. So 2 pi r is equal to v times t. T is specifically a period of going around, making one full cycle, so I'm just substituting that in for t. But we want to figure out what t is, so it's going to be, sorry, this is supposed to be an r that looks a lot like a v. Don't want to confuse it with this one. So if we divide both of them by v, that means both sides by v here. That means t is going to be equal to, I also just flipped it around, 2 pi r over v. So if we substitute this t here for this t, we know that t is equal to this, so we substitute this for this. Then we get, we're going to get 2 pi v over 2 pi r over v. So when you're dividing by a fraction, then you flip and multiply. So I'm going to just say that's 2 pi v times v over 2 pi r. So these are going to cancel and equal 1. So that's equal to v times v, which is v squared, over r. So this is our formula for centripetal acceleration. So, see? And then later we're going to use Newton's second law, which is F is equal to ma. So we can see that we have our acceleration, which is ac, and so that's v squared over r. So centripetal, or let's just say centripetal force. So centripetal force here should be v squared over r times m. So we call that mv squared over r. So that's mass times velocity squared divided by the radius of the circle. Okay. So now that we've got most of the theory out of the way, let's start doing this problem. Take a second to erase it. Okay. So we're going to start with a free body diagram, which means we're going to draw out our body, which is our car. Make it nice and big. And we're going to draw out all of the forces that are on it. So, those forces would be, we have weight here. Oh, sorry, it's tilted. It should be going straight down. We have our weight, which is mass times gravity. That's the definition of weight. And then we have our normal force. The issue is, we remember it always has to be perpendicular to the surface, but the surface is at a 30-degree angle, so our normal force is going to look like that. This is our normal force. And then we have our frictional force going like this. This is so we're going to say that, put our reference axes to say what's going in what direction. Then we're going to do it how you typically see it, where the positive y direction is perfectly vertical, or upward vertical, and the positive x direction is towards the right. You could tilt this, but we're trying to figure out our centripetal force. At some point we need to figure that out, and in order to figure that out, we have to have it be pointing directly towards the inside of the circle. So this is going to allow us to have anything going in the positive x direction to be that. So the issue is, we have mg here. That's perfectly in one of these directions. We want them to be in one of these two directions that are perpendicular to each other, or negative those. But let's say this one isn't our friction. So let's see this. We have, let me draw it out here. Basically the angle, this is friction. So we have, we know that this angle here is 30 degrees, but we want that angle to be at the like bottom end of the vector. So let's draw a perpendicular line just to see where we're at. And since these are parallel, they're both horizontal, we have a line intersecting two parallel lines. That means that these opposite interior angles are going to be the same. They're going to be congruent angles. So this one is also 30 degrees. So, let me take this away. If we remember our trigonometry, then we know that, let's just do this here. So, if we're trying to find, we know this hypotenuse is our frictional force. That's the magnitude of our frictional force. So, if we were to take cosine of 30 degrees, actually I'm going to start calling 30 degrees theta, just so I have to write one thing. Just going to say theta is equal to 30 degrees over here, so remember that. So remember SOHCAHTOA, so cosine of theta is going to be equal to CAH, so C is our cosine, and then adjacent over hypotenuse. So our hypotenuse is our frictional force, but we want to figure out our adjacent. So, oh, sorry, it's not the eraser. I'm going to find our adjacent side. So I'm going to substitute in F, for h, for our hypotenuse. And then if we're trying to find a, then it's going to be f cosine theta is equal to a. So that means right here, f cosine theta is this little component vector. So what we're doing is we're splitting the frictional force into its components that are going to be in one of these perpendicular directions. So if we do the same thing for the sine of that, it's going to be the opposite over the hypotenuse, which is f, so it's going to be sine theta is equal to O over f, and then we do the same here, so f sine theta is going to be equal to this guy. So you can see that this length here is the same as if I just moved it over here. So this one is, sorry, having a bunch of arrows makes it confusing. I'm just going to remember that this goes. So this one is f sine theta. Cool. We've got that one split up, and we only have one more to split up, which is our normal force. But we can see that our normal force is at a slightly different angle. So we have our normal force pointing like this. Actually, that looks more like looks like the wrong angle. That's a little better. There's our normal force. So let's give ourselves some guidelines of what those are. Let's pretend that was a straight line. So we can see that this one here is our theta. And this one here is going to be our theta, or our 90 is going to be 90 minus theta, or 60 degrees, because this is a 90-degree angle, and you have theta here, so 90 minus theta is going to be this angle. And also, in a right triangle, we can see that there's all the internal angles of a right triangle are going, or of any triangle, are going to add up to 180. But for right triangle, we know that one of those is 90 degrees. So that means that the other two angles are going to add up to 90 degrees as well. And so we can use that to know that sine of, let's say A and B are the two non-90 degree angles in a right triangle. Sine of A is going to equal to cosine of B. And A plus B equal 90. It's going to be the same things as, so if we say sine B is equal to cosine A. This is because the adjacent of angle A is going to be the opposite of angle B, or the opposite side, right? You can see that here. Let's say take this triangle. This side here is going to be the opposite for this angle, but for this angle here, it's going to be the adjacent side. Cool. So we know that this component here, this one here, is going to be the cosine of 90 minus theta, right? So, but we know that 90 minus theta is going, or cosine of 90 minus theta, because it's A is equal to 90 minus B. So we take 90 minus cosine of A is going to be equal, or sine of A is going to be equal to the sine of 90 minus B. So we see that we kind of have that form here. So instead of this being cosine 90 minus theta, we're going to call it sine theta. and then we're going to use, it's going to be equal to this side over n, so it's going to be equal to so this is sine theta, and we're going to say it is n sine theta. Remember how we did it with this one, f cosine theta, f sine theta. Then this component here is going to be n cosine theta. So it's the opposite of what it typically is because our angle is 90 minus theta. So I'm going to draw those in over there once I erase this. This is n cosine theta. This one is n sine theta. Let's clear out some space here. So now that we have our free body diagram and everything's pointed in the directions we want it to be, now we're going to find this symbol here is saying the addition of all things that are the forces in the y direction. So that's going to be equal to, in the y direction, we have n cosine theta pointing up. We have mg pointing down, so that means it's going to be negative because it's in this direction, which is negative y. It's minus mg. And also this one, f sine theta, minus f sine theta. So, now that we have all of this, we know that it's not accelerating up or down because the car is not sliding up the ramp. That's part of the problem. We're trying to find the maximum speed where it doesn't slide up the ramp. So we can say it's equal to 0 because there's no acceleration in the y direction. So we know that the frictional force is equal to mu s n. So let's substitute this in for friction here. So n cosine theta minus mg minus mu s n sine theta is equal to 0. And then we want to figure out what n is. So we're going to say, or in terms of all of these things. So we're going to add mg to both sides. So we have n cosine theta minus mu s n sine theta is equal to positive mg. And then I'm going to factor out the n. Here's n cosine theta minus mu s sine theta equal to mg. And then we divide by both sides by cosine theta minus mu s sine theta. So I'm going to write it down here. N is equal to mg over cosine theta minus mu s sine theta. Oof. Sine theta. Okay, much better. Okay. Just check I have everything there. Yeah. Cool. And now we've made this equation here into something a lot more useful. So I'm going to erase it. And then what we're really trying to find is the sum of all the forces in the x direction, because remember it's going to be pointing towards the radius of, towards the center of the circle along one of the radiuses. And so that means it's going to be our centripetal force. So our sum of all the forces in the x direction is going to be, we have one of them, n sine theta, and another one here. So that n sine theta is pointed in the positive x direction, and f cosine theta is also pointed in the positive x direction. F cosine theta. And then we remember that f is equal to mu Sn. So I'm going to say, oh, and remember this is equal to the centripetal force. So n sine theta plus mu s n cosine theta is equal to, remember that centripetal force is equal to m v squared over r. Cool. Now let's substitute what we figured out for n. So that's going to be equal to mg divided by cosine theta sine theta, and it's going to be n times sine theta, so this is our n, and then multiply it by sine theta. Then we're adding this, so cosine theta minus mu s sine theta, so it was n, this is n, times mu s cosine theta. Cosine theta. Let me move this mv squared over r to this side. Okay. So now that we've used this, I'm going to clear up some space. Okay. So, oh, there's something left there. So we can see that we can divide by m on both sides. So m, all those cancel out. So now we have v squared over r. So we're going to multiply both sides by r. So v squared to r, here we go. Just write out this huge thing, g sine theta, because you canceled out that m, divided by cosine theta minus mu s sine theta plus g mu s cosine theta, okay, divided by cosine theta minus mu s sine theta. Cool. Lots of numbers going on here. And then we can see that, okay, let's square root both sides because we're trying to find maximum speed. Square root of this. So the square root of that is going to be equal to v, right? So do that. And look at that. We've found an equation to figure out the maximum velocity at which the car does not slide up the ramp. So it's asking us for maximum speed, so that means it's going to be the magnitude. So if we get a negative answer, we're going to use a positive number, because that's how magnitude is. So I have prepared here, take a look at the thing on the bottom right, that huge equation. Then I have this. This is that huge equation. So I can see I've plugged in 9.81 for g, 30 for theta, 0.43 for our coefficient of static friction, and 50 for our radius. So if you want to check I did everything right, and then that's going to be equal to this number here. The thing is, let's look at the data we're given. 2,510. This has what we call 3 significant figures. It is accurate basically to 3 numbers. This last 0 doesn't count. This one's accurate to 3 as well. Because we have a decimal place and then another 0, that means that we're accurate to this spot. That means we have 3 significant figures. So we have 3, 3, and then this one has only 2 because this first 0 doesn't count. Yeah. So, 0.43, we have 2 significant figures that we're working with. So, 25.6, we can only have 2 significant figures. So we're going to round to 2 digits here. So that's going to be 25 and then 0.6 is going to round, so it's going to be 26 meters per second. So our speed, our max speed, equal to 26 meters per second. There we go.